Okay, so first page of 2.11 notes. We're focusing on non-vertical asymptotes. Now, there's really going to be two types that you're going to see. One is going to be horizontal, and the other you might hear referred to as slant. So horizontal asymptotes, certainly this is where we have a flat line that's going to occur at some y value. And for slant asymptotes, we're going to follow our ideas about end behavior. And you'll see what I mean on the later pages here. But you'll see this referred to, or you'll hear it referred to as slant asymptotes, but these together we are just calling non-vertical. Because remember, a vertical asymptote is the x value that makes the denominator equal to 0. Very straightforward. That's the one and only thing where you will find a vertical asymptote. With non-vertical, there's a little more complication to it. There's a little more work to be done. So let's start first by just thinking about y-intercepts and how those occur with rational functions. But let's start with this polynomial. This p of x is x cubed minus 4x squared minus 7x plus 10. And we all know for sure that at every level of our math, this says, hey, the y-intercept or the starting point is going to be at that constant at 0, 10. That's where we can expect our graph to cross the y-axis. That's where we can expect the constant to show up. And to remind ourselves, well, why is that the y-intercept? Because if we plugged in 0 for x, so we chose x to be 0, and we're going to, everywhere we see an x, we're going to put in 0. Because we know that a y-intercept occurs on the y-axis, which means its x value is 0. So all of these are going to cancel. Anything with the 0, the 0, the 0 is going to cancel. And our output, or our answer when x is 0, is 10. So y-intercepts always have an x value of 0, so if we plug in 0, then we can find a y-intercept. With that fact in mind, that's what happens with rational functions. So rational functions look quite different. They have a division, they have a variable on the top and the bottom, but that idea still remains, that if you plug in 0 for x, you will be finding a y-intercept. So if we pop over to Desmos, what we can see is that if we have this function graphed, well, what we should notice is that there's a vertical asymptote at x equals 2, because that would make the denominator 0, and you can see this graph is curling away from that line at 2. But if we go to the y-intercept, it's at 1.5, which if we look in the function, we have a -3 as a constant on the top and a -2 as a constant on the bottom. And those negatives are going to cancel, and 3 over 2 is 1/2. And we can see this top portion of the graph, that's not going to be approaching the y-axis at all because it's running up against a vertical asymptote at x equals 2. So if we go back to looking at our notes, we know the y-intercept is at 0, we can say 1.5, but I'm going to leave it at 3/2 or 3 over 2. And for the same reason that no matter what the function looks like, if we plug in 0 for x, we will always be finding a y-intercept. So our zeros cancel, so we have -3 on the top, 0 minus 2 is -2, 3 over -2 simplifies to our 3/2. So that's the thing in math, like once we've established something like finding a y-intercept, it works for any type of function. Linear, quadratic, polynomial, and then rational. So then we can look at these two f of x and g of x, and we can say, okay, if we were to plug in 0, we'd have these first two terms gone. So f of 0 would result in an 8 on the top. 0 times itself, 0 times -3, we'd be left with a 2 in the denominator. So that means f of 0 is equal to 4. Here, I'm just going to move this up. So we'd have f of 0 is equal to 4, which means we have a y-intercept at 0, 4. Same thing with g of x. Doesn't matter if there's 2 terms, 4 terms, doesn't matter. If this x goes in here, we're going to have a -1 in our numerator. 0, 0, 0, we're going to have a 5 in our denominator. Excuse me, so this should be g of 0. So that means g of 0 is at -1/5, which means we have a y-intercept at 0, negative 1/5.